In this course, probability and stochastic processes, in the first lecture we saw uh, some basics of probability. In this class, we will understand the concepts of conditional probability, concept of disjoint events, and the concept of total probability. Now, let's start with the conditional probability. Conditional probability is about the probability of happening of an event on condition that another event has occurred. What happens is that a new sample space is defined by condition imposing event, and we determine the chance of an event which is a subset of the condition imposing event. The conditional probability of the imposed event will be more when it gets associated with a condition imposing event. Let's see a qualitative example. Suppose that in a certain city, 28% of the days are rainy. Thus, if you pick a random day, the probability that it rains that day is 28%. That is, P of R is equal to 0.2, where R is the event that it rains on the randomly chosen day. Now, suppose that I pick a random day, but I also tell you that it's cloudy on the chosen day. Now that you have this extra piece of information, how do you update the chance that it rains on that day? In other words, what's the probability that it rains given that it is cloudy? If C is the event that it is cloudy, we write this as P of R by C, the conditional probability of R, given that C has occurred. It's reasonable to assume that in this example, P of R by C should be larger than the original P of R. Let's see a quantitative example. I roll a fair die. Let A be the event that the outcome is an odd number, that is, A is equal to 1, 3, 5. Also, let B be the event that the outcome is less than or equal to 3, that is, B is equal to 1, 2, 3. What's the probability of A, P of A? What's the probability of A given B, P of A by B? We can write P of A is equal to number of possible outcomes for event A divided by number of possible outcomes in rolling a die, that is 3 by 6 is equal to 1 by 2. Now let's see a formula for the probability of A given B, P of A by B. Let's call condition imposed event as A and condition imposing event as B. The conditional probability of A given B can be written as P of A by B is equal to number of possible outcomes of event A coming within the total outcomes of event B divided by total number of outcomes of event B is equal to number of A intersection B divided by number of B, which can also be written as number of A intersection B divided by number of S divided by number of B divided by number of S, which is equal to probability of A intersection B divided by probability of B. So we can write P of A by B is equal to P of A intersection B divided by P of B. So so I'm giving an exercise for you to apply the concept of conditional probability. I roll a fair die twice and obtain two numbers. x1 is equal to result of the first roll and x2 is equal to result of the second roll. Given that I know x1 plus x2 is equal to 7, what is the probability that x1 is equal to 4 or x2 is equal to 4? You please apply the concept of conditional probability and see that the answer comes to be 1 by 3. Now let's understand the concept of disjoint events. Events which have nothing in common among each other and which only one can happen at a time among them in an experiment are called as disjoint events. These events are also called as mutually exclusive events. In an experiment of coin tossing, events of happening of head and happening of tail are called mutually exclusive. Now, having understood the concepts of conditional probability and disjoint events, let us understand the concept of total probability. Let's explain this with an example, a qualitative example. I have 3 bags. All the 3 bags have some red balls and some blue balls. I want to find the probability of selecting a red ball. We can split into different events. Event of selecting bags and event of selecting a ball of some color. Selecting a red ball has a link with the selection of bag 1 or bag 2 or bag 3. We will name selection of bag 1, 2 and 3 as events B1, B2 and B3. We will name selection of a red ball as event A. Now we can draw the following picture. We have sample space in which we have 3 mutually exclusive events, B1, B2 and B3. We have an event which is embracing all the 3 events, B1, B2 and B3. The part of B1 of A is called as A1. Part of A in B2 is called as A2. Part of A within B3 is called as A3. We can now generalize. Let B1, B2 and B3 be mutually exclusive. Events are mutually exclusive events, and let A be an event embracing one or more than one of the events. We can write that S is equal to union of Bi, where I is the index. We can write A is equal to A intersection S. So we can write this as A intersection union of Bi's, which is also equal to union of A intersection Bi. Now note that the sets A intersection Bi are disjoint since the Bi's are disjoint. Now we can write P of A is equal to P of union of A intersection Bi's is equal to summation of probability of A intersection Bi with the variation of I is equal to summation of P of A by Bi into P of Bi, where I varies. Now let's see a quantitative example. Now let's apply quantitatively to the above said example. I have 3 bags that each contain 100 marbles. Bag 1 has 75 red and 25 blue marbles. Bag 2 has 60 red and 40 blue marbles. And bag 3 has 45 red and 55 blue marbles. I choose one of the bags at random and then pick a marble from the chosen bag, also at random. What is the probability that the chosen marble is red? We have P of R by B2 is equal to 0.6. P of R by B3 is equal to 0.45. So we can find P of R is equal to P of R by B1 into P of B1 plus P of R by B2 into P of B2 plus P of R by B3 into P of B3 is equal to 0.6. So let's have an exercise on this, a communication exercise, communication engineering exercise. An elementary binary communication system consists of a transmitter that sends one of the two possible symbols, a 1 or 0, over a channel to a receiver. The channel occasionally causes errors to occur so that a 1 shows up at the receiver as 0 and vice versa. In this problem, take transmission of 1 and 0 as B1 and B2 events. Take reception of events 1 and 0 as A1 and A2. A1 and A2. Now, probability of A1 and probability of A2 both will come under the concept of total probability. Let P of B1 be equal to 0.6 and P of B2 be 0.4. P of A1 by B1 is equal to 0.9 and P of A2 by B1 is equal to 0.1. P of A1 by B2 is equal to 0.1 and P of A2 by B2 is equal to 0.9. Under these assumptions, please calculate P of A1 and P of A2, which are total probabilities.